Welcome back. So I want to talk a little bit about how the term data science relates to other fields of science. And in particular, I want to introduce this term eScience, which to a first approximation you can think of as equivalent to data science. So while the term eScience is associated with astronomy and oceanography and biology, data science has been adopted more in business, but they involve a lot of the same concepts. So let me tell you about what's going on in science. So for thousands of years, scientific inquiry has been empirical, right? You observe the natural world, or in some cases maybe replicate the natural world in a controlled environment in the laboratory and make observations about that. In the last, few hundreds of years, science has accepted theoretical models as a valid method of inquiry, one that is reinforcing empirical methods. So, new theories suggest new experiments, and the theories help explain the observed data you get from the experiments. In the last 50 years or so, high-speed computation has emitted an entirely new method of scientific inquiry. You can simulate in the computer phenomenon that otherwise couldn't be, you can't observe directly, and you can't reproduce in the lab, and even the theoretical models become too complex to solve analytically using, essentially paper and pencil, right? But you can actually start from initial conditions and run the simulation to get a result. So this is maybe the what goes on in the interior of stars, or the shift of tectonic plates, or the evolution of the universe, or the effects on the ecology from some species dying out, and so on. So that's fine. So that's three methods of inquiry. But in the last 10 years or so, there's been arguably a fourth method of scientific inquiry, which is to acquire massive data sets from instruments or from simulations, and then explore these data sets using new algorithms and new infrastructure. And so eScience is really about massive and complex data large enough to require automated or semi-automated analysis. You can't look at it, you can't inspect it directly. Okay. And so the relevant tools here are the same as those for data science. Databases, visualization, scale-out computing, maybe even NoSQL systems, machine learning techniques, web services, and so on. Okay. So the way this idea of the fourth paradigm, there's a book that's in the reading list that you can refer to here, and there's a lot of there's some other articles in the reading list that you can also refer to. The story's been told lots of ways. The way I like to talk about this story is that science has always been about asking questions, but conventionally it was really about querying the world, right? You would sort of have data acquisition activities, experiments or field studies that were coupled to very specific hypotheses, right? You had the question in mind first and you went out and collected data. But eScience has really sort of shifted a bit where now you're kind of downloading data en masse. You're downloading the world first, putting it into some sort of a representation in the computer, and then querying that database to test your hypotheses. And so the data can be acquired independent of any specific hypotheses in some cases. Okay, and this is due in part to the cost of data acquisition dropping precipitously thanks to advances in technology, right? So the telescopes you can build now that we'll talk about in the next couple of slides can acquire enormous amounts of data at very high resolution. Okay, and in the life sciences you have sort of laboratory automation and you have high throughput sequencing. In oceanography, the sensors are getting cheaper. The models, thanks to Moore's law and advances in computing, the simulations you can run are getting bigger and higher resolution, and therefore producing larger and larger amounts of data, and so on. And so, the rate at which data can be produced has far outpaced the rate that we can analyze it or come up with the questions we need to ask about it. Okay, and this suggests a new approach to science. So let me give you some examples. So we've said that eScience is driven by data more than by the computation. Right. So some examples of the size of the data that's coming out. The Apache Point Telescope, that was the primary instrument for the Sloan Digital Sky Survey that we might refer to multiple times in this course, produced 80 terabytes of raw image data over a 7-year period. At the time, this is a pretty significant data size, and even by many standards is still today. The next generation of this the next generation project that's in the same sort of spirit as Sloan Digital Sky Survey is the Large Synoptic Survey Telescope. So this guy can produce 40 terabytes per day and will do so for over a 10-year period. So in total, 100 plus petabytes, and producing the same amount of data that Sloan Digital Sky Survey produced in over its whole entire lifetime. It can produce that over every 2 days. Okay, and so this is a pretty staggering amount of data and requires a pretty different approach. One thing I wanted to mention maybe about Sloan Digital Sky Survey, what they actually did here was to take the images, cook them, right, extract the relevant objects from it, put all those objects into an off-the-shelf relational database. In fact, it was Microsoft SQL Server, and critically host this database online and serve it out over the web. And this required a pretty significant investment in infrastructure. But as a result of doing this, of making all the data public and queryable, it became the most productive astronomy facility in history, right? So the number of papers that have been produced on this data is on the order of thousands, and the original, PIs of the project, the principal investigators of the project, had sort of maybe on the order of 100 papers in mind for the data, and the other 4,900 papers that have been written all came from external partners writing queries against this database. So just a wild, wild success. Now, the problem is that the same technology stack, and to some extent even the same approach, is difficult to apply in this case of the Large Synoptic Survey Telescope. The reason why this guy's producing so much more data is not just that it's much higher resolution and can perceive a much deeper field in the sky, but also because it's returning to the same point in the sky frequently, every 3 days. And so this allows you to look at things that change over time. So asteroids, comets, you might get a supernova, and so forth. Okay, and by comparing these images in the time series, there's all sorts of new questions you can ask. Okay, so both because of the science that they're going to do, and because of the sheer scale, and because some of the complexity of the details of how the data is acquired, the previous solution won't work. And so this is motivating a whole new area of research to study data management techniques and data analysis techniques to support this project. All right. So in life sciences, these high throughput sequencers are capable of producing terabytes per day when run continuously. And major labs that do this work, such as the Joint Genome Institute, have 25 to 100 of these machines running all the time. Right. So this is spitting out an enormous amount of data for I was going to say a variety of samples. So it may be individual organisms, or it could even be samples from the environment where there's no one particular organism in there, but there's an entire population. All right. So for a variety of uses, these guys are able to spit out the data. In oceanography, the regional scale nodes of the NSF Ocean Observatories Initiative is a project led here at UW. Ocean Observatories Initiative is a multi-institutional partnership. The regional scale nodes part is run at the University of Washington. So this project has involved laying 1,000 kilometers of fiber optic cable on the seafloor, connecting thousands of instruments in chemical, physical, and biological thousands of chemical, biological, and physical sensors, including live video from the sea floor to monitor volcanic activity. Okay, so again, the database, if not a relational database, the data sets and data infrastructure required to support this effort is significant. Has motivated a lot of new research. All right. In the information space, there's a lot of science to be done directly on the web itself, and so just the web, a single computer can read 30 to 35 megabytes per second from one disk, and so it would take about 4 months just to read the entire web. So new clusters of machines So summing up a little bit, eScience is about the analysis of data. So the automated or semi-automated extraction of knowledge from massive volumes of data. And so your main instrument for looking for answers are the algorithms and the technology, as opposed to direct inspection. There's just too much of it to look at yourself. But it's not just a matter of volume. And as we'll talk about in the next segment, this is another link back to what's going on in business, right? There's this concept of big data, and there's the 3 V's of big data that we'll talk about a little bit more next time, but let me just mention them here. Where volume, so the 3 V's are volume, variety, and velocity that you'll read about, and I'll give you where this terms came from in the next segment. But volume refers to just simply the number of rows or the number of bytes, right? The sheer scale. Variety is perhaps the number of columns or dimensions, but in science, for example, a lot of in the life sciences in particular, you'll have experiments that involve accessing multiple public databases as well as multiple sensors, your own data that you've collected and that of your colleagues. And the integration task of putting all this data together is a significant bottleneck, even when the actual scale of the data is not necessarily all that bad. Okay, so this is the complexity of the data. And then the velocity. We saw with the Large Synoptic Survey Telescope that, although the scale itself was enormous, the fact that 40 terabytes are being collected every 2 days means that the infrastructure needs to keep up with that pace. And just transferring that data from the telescope facility to the data analysis facility is an engineering challenge. Okay, and you'll also see other V's here with things like veracity. You know, can we actually trust this data? Okay, so a bit more of that next time. So to summarize here, science is in the midst of a generational shift from a data poor enterprise where you can never, there's never enough data, to a data rich enterprise where there's so much of it you don't know what to do with it. And as a result, data analysis has replaced data acquisition as the new bottleneck to discovery, right? So it's not that the cost of going out and getting the data, it's the cost of actually analyzing the data you might already have. So this is fine, but what does this have to do with business, which is probably where a lot of you are coming from and where your interests lie? Well, what we see is that business is beginning to look a lot like what's always been happening in science. So though businesses are acquiring data aggressively and keeping it around indefinitely in case it becomes useful, they're beginning to hire people that have training and skill sets that look a lot like what's been important in science for a long time, especially mathematical depth. And they're beginning to make decisions with this data that are very empirical. So we're always wanting to sort of back up every decision with a clear case based on data. And so for these reasons, I think that you can take the lessons learned in science and apply them in business, and actually vice versa as well, because one thing where science is lagging behind business is in the adoption of technology. There's been proportionally a lot less spent on IT infrastructure in science than there has in business. And so it's a great time for this. There's this cross-pollination of ideas between both fields. Okay, and so going back to this first slide that I gave, eScience and data science have essentially everything in common. So we might use examples interchangeably between the two. Okay.